difficult, and that some operational reduction, some of this reduction can actually be achieved by operational means. So for instance, a steeper descent into the airport limits the area over which the high noise is experienced. And if you can keep that inside the airport perimeter, then the only people you upset are those people in the airport, and since they want to fly anyway, they're probably not too upset. So our Trent 1000 engine is 12% more efficient than that first engine. You can see the XWB is even more efficient, as I said earlier. Now, the designer is wrestling all the time with this. It's not possible to minimize all of these things at the same time. There are basic laws of physics that say if you push down fuel burn, something else will pop up and get a bit worse. So for instance, engine pressure ratio. At the core of the engine, we compress the air to 50 atmospheres. It gets very hot. So the higher that pressure, the more efficient the engine. So that's a good thing. But as it gets hotter, then when you add the fuel, you create more oxides of nitrogen because you're putting more energy into fusing that air together. So the NOx will get worse as the CO2 gets better. Bypass ratio, the amount of air that passes down the outside of the engine compared to that goes through the core of the engine. Again, if we make that bigger, we know the engine gets more efficient, but the drag of the aircraft goes up, so we burn more CO2, but then the noise comes down. A big fan turning slower makes less noise than a small fan turning fast. And although I'm not going to talk more about it today because it's still a very contentious area, the creation of cirrus clouds and contrails from aircraft itself can create global warming, and by flying lower and by flying through different air paths, you can reduce the amount of contrails produced, but at the same time, you'll burn more fuel. So no free lunch in any of this is the short message. Alternative fuels, I mentioned biofuels. Again, as I say, Malaysia is particularly strongly placed and has some excellent research in this area, potential to make biofuel directly from palm oil and to make biofuel from algae, many other projects going on here. We've said all along that biofuel must first of all be safe. You could fly an aircraft on vodka if you wanted to. Not the pilot, but the engine itself. You could fly an aircraft on vodka, but that wouldn't be safe for the passengers. It wouldn't be safe for the aircraft, and actually the tanks would freeze up at high altitude, which wouldn't be good at all. So you do need to make sure that any biofuel has the same physical properties as today's fuel. And in fact, most of the certification at the moment is limited to just 50% biofuel mixed with conventional fuel. So at the moment, you're not allowed to run totally on biofuel. The second one is sustainability. Not everything that says bio on the can is good for you. And you have to really look in great detail. If somebody says, I've got a great biofuel, then you have to say, well, how did you make it? How much energy did it take to create this fuel? How far did you transport the biomass by road before you turned it into a biofuel? And all of those things are actually taking away. The whole philosophy of biofuel is that when the plant's growing, it sucks in carbon dioxide from the atmosphere. When you then turn that plant into fuel, you let the oxygen, the CO2 back out, and that should be a neutral process. But if you create yet more CO2 in creating the fuel in the first place, you're not necessarily doing the right thing. And then the other aspect of biofuel is that it shouldn't compete with people for food or water. We've seen in history how cash crops in Africa, tobacco, for example, has made countries richer but people poorer. People who used to be able to grow their own food then have to import food because the country's using too much of its land for cash crops. So getting that balance right is essential as well. The final area is what I call industrialization. A number of times somebody comes to me and says, you know, I have this magnificent biofuel, you should test it. And we test it, and we say, that's fantastic. You know, can I have 60,000 liters next week for a full test? And they say, 60,000 liters? It took 2 years to make that glass full. So it's not easy. But it is part of the solution, as I've already showed you. So let's have a look at the jet engine, because as I said, it really is, I've been around them for 36 years now, my whole time with Rolls-Royce, but I'm still amazed by them, and hopefully I can convey to you some of the amazing technology that's in there. So some great things are happening. We suck in about a ton of air to a modern engine. Actually, most of that doesn't go through the core of the engine at all. Most of it goes down what we call the bypass and produces most of the thrust for the aircraft. So think of this fan on the front just like a big propeller. It's pushing the air backwards and therefore pushing the aircraft forwards. A small part, about 10% of the air, goes through the core, and the Rolls-Royce product is unique in that it has a three-shaft design. So this big fan on the front is turned by a low-pressure turbine at the back. This first set of compressors is turned by its own intermediate pressure turbine, and then at the core of it, you have the high-pressure compressor turned by its own high-pressure turbine, and this is where all the magic happens. So you suck a ton of air in the front, you add just 7 pounds of fuel per second to each ton of air, and that creates the magic. A little controlled explosion goes on here. The temperature, by the time you get to this point, is already around 700 degrees Celsius. So that's, steel is glowing red hot at that temperature, and that's just by compressing the air. Like if you put your thumb over the end of a bicycle pump and press hard, your thumb gets quite hot. That's all that's happening here. Just basic thermodynamics is getting us up to 700 degrees centigrade and 50 atmospheres of pressure. So less than 1 atmosphere here, up to 50 atmospheres. We add in the fuel, and of course the temperature goes up still further. We add another 1,000 degrees to the fuel, and that energy is then released by driving these turbines until we've stripped out as much of the energy as we can by the time the air comes back out the back here. So it's really an incredible piece of technology, always limited by materials technology. So materials that can stand these high temperatures and pressures have been the limiting factor, and developing new materials has enabled each new step change. Right back to Frank Whittle's time. So I met the great Frank Whittle twice in his life. And the second time I was talking to him about the jet engine, I said, you know, you look at all the magnificent things that have happened. People can fly halfway around the world in a jet engine. There's a saying that you'd be mad to fly more than halfway around the world, but that's not the matter. But you can fly halfway around the world, you can carry lots of people, all of these things. Somebody from Boeing actually said in 1912 that the most people you would ever see in an aircraft was 12. Now you have the Airbus A380, which all economy could have about 700 people on board. So some amazing things have happened. But Frank said to me, the one thing he didn't envisage was that a jet engine would ever last more than 1,000 hours. So less than a year's life, which was the sort of life from those early jet engines. Now, Rolls-Royce engines, the record is 42,000 hours on the wing without a service. Imagine driving your car non-stop for 12 years, that's without taking it to the garage. That's the sort of thing we achieve today. Oh, what happened? Better. Never let a chief of technology loose with the technology. Very dangerous. So, imagine you could hold the entire power of a Formula One racing car in one hand. That's what this guy's doing here. That single blade from the high pressure turbine produces the same power as a Formula One racing car. So that in itself is pretty incredible. There are some even greater facts around it. The temperature, 1700 degrees C, is actually 400 degrees hotter than the melting point of the metal. So fundamentally unsustainable. You've got this blade sitting there in a gas stream that's trying to melt it and flush it out the back of the engine. And it's only protected by air cooling and sophisticated ceramic coatings that save it and protect it. The tip speed is over 1,000 miles an hour, so faster than the speed of sound. And the stresses are equivalent to hanging a double-decker bus off the end of every single blade. So you imagine all that, and that's really driving the materials technology to the limit. This blade is made out of just one crystal of a very sophisticated nickel alloy, grown in the shape of the blade. So that gives you the ultimate in material strength and properties. So I'm now going to take you on a little journey through the jet engine to describe in more detail what's going on. And the video should start automatically, but it's not doing. Could you start the video? Okay, so here we go. We're a little molecule of air. We're flying in the front, and we're going to get sucked in with a ton of air into this engine. Most of the air is going to go down the outside. but we're going to go have a look what's happening right inside the engine. So as we go through the big fan blades, already we're getting compressed by that fan, about 1.8 atmospheres and 100 degrees more temperature, into the guide vanes and down a steep slope into that first stage of compression, the intermediate pressure compressor. And here we can see the blades coming up, first stage, second stage, 8 stages in total, compressing the air to around 10 atmospheres and about 400 degrees centigrade. And so we carry on through till we get to the back of the intermediate pressure compressor, which is coming up shortly. And then down another steep slope, and now into the high pressure compressor. So this, very small blades because the air is getting squashed down and smaller. And as we go through these 6 stages of high power compression, then we're getting squashed and squashed until we're at 50 atmospheres of pressure and 750 degrees centigrade. So as we come to the far end, we can see ahead of us the combustor. And that green stuff in there, that's the fuel being added. So we're going to go in there, we're going to meet a particle of fuel, and bang, we catch light, we go on, and then as we look around, we can see everything's glowing red hot. It's pretty warm in there. And as we come out the back end, the air's at 1700 degrees centigrade, and we go into that first stage of turbines so that you can see the little cooling holes going by, spraying some cool air onto the front, and then into the intermediate pressure turbine. And finally, as we go through the back, we come to the low pressure turbine, 6 stages of low pressure turbine, all turning that big fan on the front. So the big fan is really what's pushing the aircraft forward. In Frank Whittle's jet engine, it was the hot gas from the jet itself that pushed the aircraft forward. Now that's doing a very small amount of the work. So we survived, we come out the back, and we turn around and say goodbye to the aircraft, and the aircraft can go on its way. So the air's been pushed backwards, the aircraft's been pushed forwards, and off it goes. So I hope you enjoyed that short journey. If we could go back to the presentation. Great. So how can technology help us to improve still further on that jet engine, and what's the path we're taking to get through that? We think of our technology in what we call visions, Vision 5, Vision 10, Vision 20. You can think of them as generations or time horizons. 5 years in our business, Vision 5, is a very short time. It's the time from starting to design a new aircraft to certifying it and putting it into service. So you really don't have a chance. If somebody comes with a sticky black mess in a test tube and says, this could be your next fan blade, you don't have time to try that out in the 5 years. So Vision 10, that's when we're building whole engines as demonstrators, technology demonstrators, in that 10-year window to prove that that technology is safe, isn't going to kill people, is really worth having. And Vision 20 for the long horizon, that's when we can work with our research partners on sometimes what seems some crazy ideas for the future, but as you get nearer, they become stronger and more realistic. So we lay out our technology in that way for the future. So here's our latest, one of our latest engines, the Trent 1000, and you can see some of the ways that we're able to contribute to efficiency. The hollow fan blade here is very lightweight, very robust, very strong, and very efficient at doing that first stage of compression. All of the core components are optimized for their aerodynamics to make them as efficient as possible. And interestingly, this fan case that has the job of stopping the blades if one of them does break, that's shortly coming to be manufactured here in Malaysia with a deal we've done with UMW, which I'll talk about later. But if we look at the next engine, the XWB, just 4 years after the Trent 1000, then all of these are new technologies. So you can see the pace at which we have to inject technology in every new engine that comes along. So an even more advanced fan blade, intelligent health monitoring, 3D aerodynamic design in the compressors, what we call blisk technology. So conventionally, compressor blades slot into the disc and are just held in there by centrifugal force. But if you weld the blade to the outside of the disc, you can make the whole disc 30% lighter because you don't need those location features. So that's increasingly what we're doing with what we call blisks. By only using the cooling air when you need to and switching it off when you don't need it or reducing it, then you can save fuel. The low emissions combustor is coming along, as I said, advanced materials in the turbines, and some new manufacturing technology around the HP turbine. So all of that in just 4 years into that new engine. But the development of that technology had taken 10 or 15 years before that. So as we go forward, this is today's latest engine, the Trent XWB. As we move forward, we're going to change the internal architecture of the engine quite a bit in what we call the Advanced. So that's going to be available in 2020. Still a 3-shaft engine, but with a different balance of work between the intermediate pressure compressor and the high pressure compressor. Pressure ratio going up is still further to 60 atmospheres. That means the whole core of the engine's getting hotter and higher pressure. And fuel burn compared to the first Trent engine, about 20% improvement. And we're already looking beyond that to 2025, a new engine called the UltraFan, so a much bigger fan still, quieter, more efficient than before, but now with a very high bypass ratio, so 15-to-1, 15 times as much air going down the outside as goes through the core, compared to around 10-to-1 today. And 70 atmospheres now at the core and another 5% of fuel saving. So 5% may not seem a lot, but 1% of fuel is worth $1 million per aircraft per year. So an aircraft burns a lot of fuel. And similarly, it's worth a lot of tons of CO2 per year. Okay. So this is our new engine, the Trent XWB, and you can see the internal architecture. And this, again, I think the video is not going to work, but anyway, as we go from the XWB, it looks like this, to the Advance, then the critical thing is we've reduced the number of intermediate pressure compressor stages, we've taken that out, and we're doing a lot more work now with 10 stages on the high power compressor. So a big change in the balance, and then as we go from that to the UltraFan, we need all these new technologies to help us get there. Very high bypass ratio enablers, advanced core architecture, new materials. As I said, all the history of the jet engine's been dominated by new materials. So ceramic-based composites used right in the heart of the engine. Ceramics can take even higher temperatures than the metals. New lightweight materials for the back end of the engine, still very hot, 600 degrees, 700 degrees centigrade, but using titanium aluminide instead of nickel, you save a lot of weight. And lean burn combustors, so the cleanest combustor we have to meet those 2020 targets. Lightweight structures such as the fan, moving from a hollow titanium fan to a carbon composite fan. Intelligence in the engine. High power computing plays an important part. Being able to build and test an engine inside the computer instead of making it and testing it in reality saves time and saves a terrific amount of money in the test program. So investment in high power computing is a critical enabler for all this. And then you have to be able to generate the aerodynamic predictions that go with that. And finally, another big and important area is advanced manufacturing. This again is an area where we want to work together in Malaysia, a program we call the Factory of the Future, to look at some of these manufacturing technologies for the future. So let's just look in detail at one or two of those. This is our composite fan blade. So this is a carbon composite material. It's made of polymers with carbon fibers running through it to make it strong. It's very good and does the work in a much lighter way, particularly as you get larger than the titanium blades. The only thing it's not good at is stopping birds. So the carbon composite, if you get a bird in the front, is going to break up. So we still use some titanium, which is why we call it the composite titanium fan blade, just to protect the leading edge, enough to deflect stones and birds and anything else that tries to get into the engine. And as I said, in the R&T world, we have to not only just create the technology, but prove it. So we built a whole fan set, and then last year, about a year ago, almost exactly, we flew it for the first time in Tucson, Arizona, on our own flying test bed. And you can see the 747 aircraft here. And you can actually see the terrific difference. These are the Rolls-Royce RB211 engines from 30 years ago. And this is today's engine. You look at the difference in size. It's huge. In fact, we had to jack the undercarriage up a bit just to stop it scraping along the floor when it landed. So it was quite a challenge. And manufacturing technology. This is one of the structures. It's that front structure we went through just behind the fan that goes down into the engine. It's about 1.6 meters in diameter. And this, we think, is one of the largest objects yet made by what's called 3D printing. So 3D printing's been around for a while, making things out of plastic to demonstrate design concepts. But now you can do 3D printing directly in metal, with titanium, with aluminum, with steels. So you can, once you can design something in the computer, you can just tell the machine, okay, print me one of these. And this vane structure, which as you can see was on the front cover of Flight magazine in March this year, is made of titanium, printed with electron beams from powdered titanium. And really it liberates the thinking of the designer, because many of the traditional manufacturing technologies like casting and forging, they constrain the design in some way. But with 3D printing, if you can imagine it, you can make it. You can make spheres within spheres without being able to see what's happening in the center. So really very exciting technology for the future. And going beyond the UltraFan, then we can see other types of engines that may happen or may not happen. As I said earlier, prediction is very different. But what we call the open rotor is really going back to propellers. So we didn't go away from propellers because they were inefficient. They are actually quite efficient. We went away from propellers because they couldn't fly high enough and they couldn't fly fast enough. Now, if you put two propellers in a row, one of the problems with a propeller is as the air goes through the propeller, the air itself starts to turn around. And that momentum that's turning the air around is not terribly useful. It's trying to flip the aircraft over. It's not pushing the aircraft forward. But if you put another propeller right behind it, turning in the opposite direction, that'll continue compressing the air, but straighten it out again. So you now get all the momentum, and you get something that can fly as high and fly as fast as a conventional jet engine, but with an even bigger fuel saving, because the larger the mass of air you can put through, if you grow this fan up to this size, this could be 4 meters in diameter, then all of this outer casing gets too big and heavy, increases the drag of the aircraft. If you get rid of that casing, you make a lighter engine, but a more efficient engine. So what's the problem? Why don't we just do that? Well, unfortunately, as I said earlier, there's no free lunch. So if you make something more aerodynamically efficient, it will have penalties elsewhere. These are some of the concepts we've been working with. So we've worked with Airbus in particular on concepts like this, where the engines are mounted at the rear. And we've worked with Boeing on aircraft where the engines are mounted conventionally. But again, because these are so big, you wouldn't be able to get the aircraft on the ground unless you lift the wing up on top of the aircraft. So looks interesting, certainly a challenge to the designer, not just the engine designer, but the aircraft designer, but can be done. And these are some artists' impressions of future aircraft with that technology in it. This is not an artist's impression, it's a real photograph from 1986. At that time, they were called prop fans, not open rotors. They were much smaller than the ones we're talking about now. But here you can see one actually developed by the Allison Engine Company, which I mentioned that Rolls-Royce bought. And at that time, we were looking at fuel efficiency. Nobody'd heard about global warming or saving the planet. The reason at that time was that oil had gone above $30 a barrel. Nobody thought the world was going to end. So we all started investing, every engine company, in these new, more efficient engines. And then oil prices came back down again, and everybody forgot about it and switched it off. So there's nothing new, really. But with modern technology, we can make the fans much bigger and quieter and achieve the same endpoint. So what's the problem? As I said, well, here's today's aircraft. This is a chart of noise. Noise is getting lower as we go to the right, and it's in decibels, again, a logarithmic scale. And here's the fuel consumption. So fuel use is getting better as you come down the chart. So ideally, you want to be down in this bottom corner here. Here's a typical aircraft today, the Boeing 737, the Airbus A320. It has to meet Chapter 4 noise requirements, so it gets the rest of that. And we've used that as the datum for fuel. So if we go into the past and look at the older aircraft, then they were much noisier than today, nearly 10 decibels more noisy than today. But that rotor aircraft we demonstrated was indeed more efficient by about 15% compared to a conventional engine. So we know the efficiency is there, so it's the other way around. That's the old MD-80, and this is the open rotor powered aircraft, as I say, about 15% more efficient. Now, as we go into the future, we could do the most advanced turbofan, and we'd finished up here, probably 20 decibels quieter than today's engines that are flying around. And we could save quite a bit of fuel, probably around 15% relative to today's engines. But if we do the open rotor, we can never make it as quiet because there's nothing to catch the noise that comes off the tips of these fan blades. So once it creates some noise, it'll just propagate until it gets to the ground and upset people. But look at this, it's quieter than today's aircraft. So we're not saying we're going to make a noisier aircraft, we're saying we could make a quieter aircraft than today, but not as quiet as technology would allow it to be. And that's the political debate that's going on out there. Frankly, it's not a technological debate. We know how to do both of these for the future, but somebody has to make some tough decisions. Do you want your aircraft as quiet as possible so you don't upset people near airports? Or do you want your aircraft quieter than today, but producing 10% less carbon dioxide and helping to save the planet? So I'll leave that for the politicians to discuss. So there are all sorts of other technologies out there, the open rotor, more integrated design. This was an interesting design. It was Rolls-Royce, Cambridge University, and MIT doing something called the silent aircraft. So make an aircraft as quiet as possible. It was never totally silent, but it was a very, very quiet design. But again, the fuel efficiency was not good. So we're having this fight all the time between trying to, by fully embedding the engines inside the aircraft, you can absorb most of the noise that comes out, but it'll never be as quiet. Advanced cycles, we know how to, we're nearing limits on the fundamental gas turbine efficiency, but we know from ships we do with advanced gas turbines, with intercoolers, with recuperators, that we can make them much more efficient. But those devices today are very big and heavy. You'd never get an aircraft engine into the world. So one of the technology areas is to look at advanced heat exchangers, very compact heat exchangers, so you can play with the heat in the gas turbine cycle, manage that heat efficiently and effectively, and make the engine even more effective. New forms of combustion. Today, the combustion just gets the air hot. It doesn't contribute any useful work. But pressure gain combustion, pulse detonation is another form, can actually get some useful work out of the combustor, so you can drop some of the input compression stages. And already on military engines, we're looking at morphing technologies that can physically change the shape of the engine depending on whether you want to fly very fast or fly so slower and save fuel. So physically changing shape as the engine flies. So let me finally talk a little bit about collaboration, because I think that's something of interest. First, an example from Europe. I'm the chairman of the board of a program